Okay. All right. So hello everyone. Hello everyone again. Now I'm going to switch to lecturer mode and not administrator mode. Okay. So this lecture series is going to be about general relativity. Okay. So general relativity is an amazing and beautiful subject. It's really sort of the a description of our universe at the longest possible scales, and it tells us about many beautiful and profound things. The most important idea in general relativity is that the thing that we call gravity is actually secretly something different. Gravity is actually the curvature of space and time. Okay. This is the central idea of general relativity. And what we're going to do is we're going to teach you what this means and how you can use it to calculate things about our universe. All right. That is the goal of these lectures. Now, these ideas, curvature of space and time, might sound a little bit complicated. And really, we're going to spend a lot of time telling you how to think about curvature for manifolds, curvature of manifolds. What does that mean? How do you talk about curvature? And we'll develop a fair amount of mathematics for that. So we're going to develop that mathematics, then we're going to use that mathematics to understand how to think about gravity in a fundamental way. So today I'm going to start by giving you some background on what GR is and why we need GR. And then we will eventually get into some of the maths involved in describing the curvature of space and time. In particular, today, if we're lucky, we will get all the way to an introduction to the idea of the metric, which is the fundamental degree of freedom in general relativity. Okay? Okay, but we'll get there slowly. What we're going to do first is I'm going to first try to explain to you why do we need general relativity? Okay, why is GR needed? Now, in some sense, in our progression as scientists or as human beings, our idea of what gravity is usually changes with time. Okay, so let me first ask everyone, instead of getting into what is GR, let me just ask you a more general question, which is what is gravity? Okay. Now, this question has a different answer, sort of depending on how old you are, right? So the first answer that you learn when you are very, very young, so this is something that children know, okay? Children and apparently the flat Earth community, which is amazingly enough a real thing. Gravity is basically just a force that magically pulls everything down, right? So what is gravity? Gravity just magically pulls things down. Okay, so imagine here you are, this is a child version of you. You are standing and then you drop something like a toy, and that toy will then fall to the ground and sit there. In other words, gravity is the thing that makes everything go downwards. This is our first idea of gravity. Okay, it's very, it's very sort of basic. This is actually how gravity manifests in our everyday life normally, but that's sort of the simplest thing. Now, as we become older and more sophisticated, we learn that this is not the right idea of gravity. Okay, gravity is obviously not that. What does down even mean? Like, what is down really? Down is a strange concept. And when we're in high school, we learn something better, right? In high school, we learn that gravity does not pull everything down. Gravity pulls everything towards everything else. It's a universal attractive force. Okay. And not only that, there's a formula for it. If you have one mass m1 and another mass m2, and they're separated by a distance r, then there's a force for the gravitational pull between these two things. Sorry, there's a formula for the gravitational force between these two things. And the formula is minus g m1 m2 over r squared in the direction of the other guy. Okay, this r hat just means in the direction of the other thing. Okay, so this is Newton's inverse square law. Everyone knows this, I think. And we realize this is a more sophisticated version of gravity than above, right? We used to think gravity pulls everything down, but that's not true. What's just happening is that down is the direction of the Earth. The Earth is so much heavier than everything else around us that it pulls everything towards the Earth. Okay? And this is, of course, better than the previous flat Earth idea of gravity pulling everything down because you can explain more things with it, right? In particular, the same force that keeps you in your chair is the force that keeps, for example, the Earth in orbit around the sun. Okay? the same force. And you can calculate all kinds of things. You can do like orbits and all kinds of stuff using this. All right. And everyone, I think, has done many calculations of this idea, and you know what this means. Okay, so this is our high school understanding of gravity. But now we're getting older still, right? Now we're all undergrads or master students in this course, more or less. And we realize that this is again a more sophisticated way to think about gravity, right? Which is that you see, forces don't happen magically. In our undergrad, we typically learn that forces are mediated by fields. Okay? Forces don't just magically happen. Instead, objects move around in fields, and those fields pull on those objects, right? Now, most of us in our undergrad, we learned this the most explicitly, not in the context of gravity, but in electromagnetism. So because electromagnetism is a useful thing to keep in mind as we do more complicated things, I'm going to just remind you how E&M works, and we'll build on that going forward. So everyone, I think, knows the equations of electrodynamics, which I'm writing down here, in units where many things are 1. Speed of light will always be 1 in this course. C is always 1. And I've also set a few other things to 1 in this thing. That doesn't matter. Okay. So these are the equations of Maxwell's electrodynamics. Okay. And I think everyone knows these equations. But what do they mean? What they mean is that if you have some sort of charge here, this charge will create some sort of field. Okay. And the field is something which is valued in space and time away from the charge. Okay. So the field has some value everywhere. And then other charges feel that field. Okay. And then those charges move around under the influence of the field. So the field is what mediates the force. Okay. Now, this is, I think, pretty familiar to people from electrodynamics. You can, of course, also do this for gravity. So if we do this for gravity, we can also do this, and we get what's called the Newtonian potential. Are people familiar with the Newtonian potential? The Newtonian potential is defined in the following way. It's a field that lives in space and time. I'm just going to call it phi, okay? And the Newtonian potential satisfies the following equation. The Laplacian of the Newtonian potential is equal to 4 times pi times g Newton times the mass density at a particular point, okay? So here rho m of x and t is the mass density, okay? And phi here is the Newtonian potential. And finally, this grad squared is partial x squared plus partial y squared plus partial z squared, the regular Laplacian, okay? Now, what does this mean? What this means is that if you have some sort of a mass, okay, so here's a mass. In the vicinity of this mass, this rho m takes some non-zero value. Okay, it has some non-zero value here, which means that it sources the Newtonian potential, and the Newtonian potential takes on some value which you can solve for. Okay, so you can solve for phi of x and t everywhere in the vicinity of this mass. Okay. And now if you have another object, another mass here, then this mass will feel a gravitational force, which I'm going to call Fi. Sorry, this should be M. And the gravitational field that this thing feels, the gravitational force that this object feels, is given by minus M partial I phi at x and t. Okay. I'm mixing my notation here. This is because I've not introduced the right notation yet, but this just means that the force due to gravity, I'm writing it in two different ways. These are the same equation. The force due to gravity is the gradient of the Newtonian potential. Okay. Okay. Now, and now you can convince yourself, if you haven't done this already, that this is the same idea. If you actually solve for this field phi in the presence of a point mass, this is basically the same idea as Newton's law. Okay, we just written it in terms of a field called the Newtonian potential. Okay. All right. So, and this is probably where most people have stopped their study of gravity. All right. This is pretty much as far as you can go without introducing general relativity. Now, in fact, many undergrad courses actually don't even discuss the Newtonian potential in much detail because it doesn't really do that much for you that the Newton's law doesn't already do. Now, however, this is actually not satisfactory. Okay. This formalism has some problems. In particular, this formalism, the formalism of the Newtonian potential, is not compatible with special relativity. Okay. So remember, what is special relativity? Special relativity is the idea that everything, that physics is the same in all inertial frames of reference. You can boost and physics will still be the same if you're moving at constant velocity. And that has very deep, far-reaching consequences, which you should mostly know about. Okay. And one problem with this is that this equation that I just wrote, this equation right here, is simply not compatible with special relativity. Now, there are various ways to see this. You can imagine doing a Lorentz transformation on this equation, and you will see that it doesn't work anymore. The left-hand side is no longer equal to the right-hand side. But this is sort of a very basic way to see this is incompatible with special relativity. And the way to see that is that if you write down this equation here, let me just write it again, so I have to stop scrolling. What was it, 4 pi g. Now, this tells you how the field responds to the mass. Now, notice that the time that appears here is exactly the same time that appears there. Okay? So now imagine that you are here, okay? And you do something crazy, wave your arms around, you change your mass distribution in some crazy manner, you jump around in some way, okay? If you do that at some time t, that information will instantaneously appear at some faraway location. You can have your phi evaluated really, really, whoops, what happened there? You can have your phi evaluated really far away, and the information about this crazy change in jump will appear instantly here in the phi measured far away. Okay? In other words, this equation implies that information goes instantly from one point to another. Now, is that possible in special relativity? I realize that you have to write this in the chat, but the answer I'm looking for is no, it's actually not possible. And the reason is that in special relativity, everything has to go slower than the speed of light. Okay? There should be no way to send information faster than the speed of light. But if this equation was always correct, then it would be possible. Okay? It'd be possible if you want to send information faster than light, all you have to do is just sort of move some mass around and have your friend who's really far away just carefully measure how the gravitational field changes. Okay? Now, we should ask, why did this happen? And if you think about it, what really happened was that there's no DDTs in this formula. Okay. If there was some DDTs in this formula, then there would be a sort of lag, and then you could analyze the wave equation and check that everything would go slower than the speed of light. So one problem is that this formula treats space very differently from time. This equation has spatial derivatives but no time derivatives. And that's kind of a sign something is wrong with the equation. It won't work in special relativity. So our goal is to fix this equation to make it consistent with special relativity. Okay. And the really amazing thing that's going to happen is when we do that, we're going to find that gravity is actually the curvature of space and time. Okay. So by just trying to make a consistent theory of gravity with special relativity, we'll find out all kinds of deep and amazing and beautiful things that we might not have expected. Okay. Okay. Now I'm going to pause for a second to take a look at the questions that have appeared. So let's see. Okay. So one question is, does he write everything with caps lock on? And the answer is yes, I do. I'm not screaming. It's just this is just what I do. Yeah. My handwriting in lowercase is much messier. That's why. Okay, next question. Is this a law or can we derive the expression for force from any other fundamental equation? That's an amazing, amazing question. Thank you for that. When you learn this in high school, it's given to you as a law, right? Newton's law of gravity. However, it turns out to follow from a more fundamental equation, which we're going to do. Okay, so that's a great question. Hang on to that. Okay. Fundamental law, yeah, it's a law, but it does, they're both true. It's a law, but it does follow from a more fundamental equation. Okay, good. Indeed, it's called the Poisson equation, and then I don't quite understand the rest of this. And good. It's a good question. Can't it be fixed up with concepts like retarded time, like we do in electrodynamics? The point is that this equation does not need retarded time to be solved. That's the issue. You can solve this equation instantaneously. However, electrodynamics is consistent with relativity, and so you need to use retarded time to solve those equations. These need retarded time. This one doesn't. Okay. That's why this one is wrong. I mean, it's not wrong. It's just not good when things are moving at the speed of light, as we'll see. Okay. Okay. Fantastic questions. Thank you, everyone. And now we're going to keep going, and we're going to soon get into the math. But before we do that, I'm going to give you one more sort of brief heuristic thing. Which is I want to now heuristically convince you that space and time are curved through an analogy. Okay, this is a sort of pop science level analogy. It's not very sophisticated, but it is correct. I'm going to lie to you once, and then I'll tell you what the lie is, and then in 3 lectures you can understand the lie yourself. So I'm going to now try to heuristically convince you. Heuristic. I'm going to try to convince you that space and time are curved. Okay. So I need to convince you something is curved. So before doing that, I'm going to try to first ask you about an easier problem that you're familiar with. We all live on the Earth, okay? And the Earth is curved, famously. Okay, so here, this is a terrible drawing of the Earth. Okay. Now, how do you prove that the surface of the Earth is curved? How do you do it? Any thoughts? Does anyone want to give me any suggestions? How do you prove the surface of the Earth is curved? Okay. There's some good ones here. Let's see. Horizon. Someone has mentioned that you should look at the horizon. That is a great answer. That is the most practical way to do this, but it doesn't. It's not good for my analogy, so I'm not going to do that one. Indeed. Up is not the same for everyone. Yeah, that's true. It's sort of hard to sort of talk about the sum of the angles of a triangle. That is a great answer. It's what I'm really going to do, but a little bit differently. I'm getting many of them. Go around the entire globe. That's pretty much what I'm going to do. I'm getting lots of them. Everyone is actually getting to the right answer already. Yeah. Seeing shape from the seashore, same as the horizon one. Check for Euclidean geometry. Shadow from the sun, check parallel lines. This is all great. You've all given me lots of answers. So I'm going to summarize all of these in the form of an experiment. Okay. So here's an experiment that you can do, which is basically testing all the ideas that everyone is saying. Check for Euclidean geometry. And the way in which we're going to implement this is the following thing. We are going to do this by taking two airplanes. So here's one way to do it. Okay, it's what you're all saying this basically. Take two airplanes. Okay, it's a bit expensive, but we're going to do it like this anyway. So take two airplanes. Okay, so here's airplane one and airplane two, and tell the pilots of each airplane to go in a straight line. Okay. So I'm going to tell this pilot, go in a straight line, and tell the other pilot to go in a straight line. It's a very expensive experiment, this one. Okay. But it's worth it because we're going to prove the surface of the Earth is curved. So what happens? Now, first of all, imagine that the Earth was flat. Okay. These two pilots, they're deviated. There's an angle theta that separates the two of them. Okay. Now, if the Earth was flat, then what would happen? The two pilots would just keep flying forever, and they would never meet again, right? If they're flat, then the two pilots never see each other again. Pilots never meet. Okay. But that's not what happens on the surface of the curved Earth, right? Because if the Earth is curved, then if you tell two pilots to go in straight lines, they will meet again after some time, right? At the other end of the Earth. Okay. But if it's curved, I cannot write the word curved. If the Earth is curved, on the other hand, even if the pilots try to go in a straight line, because the Earth is itself curved, the meaning of straight isn't quite right, and they can each try to go in a straight line as much as they can, and they will again meet after some time. Pilots do meet again. Okay. So this is one simple and expensive way to prove that the Earth is curved. Okay. And I'll notice that many of the responses in the chat were talking about check for Euclidean geometry, looking at angles and so on, check parallel lines. This is what we're doing. I tried to make two things that would go away and never again converge, and they don't. They do again converge. The notion of parallel is a bit different. If the Earth is curved, then we're all quite used to this. Okay. Okay. Now, let's talk about something different. Okay. Everyone keep this in mind, and we'll talk about something a little bit different now. So now we're going to return to gravity, and I want everyone to imagine the following thing. Imagine you are standing on the surface of the Earth, okay? So here's you, and I'm going to call this direction that's up, Z, okay? Now, I'm going to draw a picture of the trajectory that we take through space and time. So here is a picture of you in Z and time, and now you're just standing on the Earth, you're not moving or anything, so this is your world line. Okay. You don't move with time, so your world line is just a straight line in space in time at one fixed value of z. So this value of z is z naught, and you're sitting at that value of z. Okay. Okay, everyone happy with this picture? I'll just give you a second to stare at this and make sure you're happy with it. We're not moving, I'm just sitting here, so I'm at one fixed value of z for all time. Okay. Now, I want you to next imagine that you take a ball, okay, and throw the ball into the air. Okay. Now, what happens if you throw the ball into the air? So first, if there was no gravity, let me actually draw this picture again over here. If there was no such thing as gravity, what would happen? So you are standing here. If there was no gravity and you threw the ball into the air, then the ball would just start moving at some constant speed in the z direction and keep moving at that constant speed. Nothing would change. In particular, you and the ball would never meet again, right? The ball and you, that's it, right? You never meet again. On the other hand, if you are near the surface of the Earth where there is gravity, that is not what happens, right? If you throw the ball into the air in a world with gravity, in every world, then the ball starts out going away from you, but it feels the force of gravity and it comes back and you meet the ball again, right? You throw it in the air, it goes up and it comes back to you. Okay. This is what happens with gravity. Now, I want you to compare these two pictures that I just drew with no gravity and with gravity with the two pictures of the planes that were moving in straight lines on a flat space and on a curved space. In the one that is curved, the two planes, even if they try to move in a straight line, they do meet again. And over here in a world with gravity, if you try to move in a straight line, you will again meet. Okay? So it turns out this analogy is actually correct. The reason why you meet the ball again in this thing is really because space and time are curved. And it's really the exact same reason that the two airplanes would meet again. Okay, you can calculate the various things coming from the curvature and show that it's coming for exactly the same thing. And what we're going to try to do for you today, or rather over the weeks to follow, is to give you the tools to understand very carefully the analogy that I've got given here between straight lines in space and over here straight lines in space and time. Okay. Now, I have lied to you in one way. As you will see as we go, it turns out this path, the path of the freely falling ball, is a straight line in space and time, but the path of you, as you stand here on the earth, is actually not a straight line in space and time. So I'm telling you, this is straight and this is not straight. That might seem surprising from the way I've drawn this picture, and what we need is a more refined notion of what straight means, and we will get there as we go. Okay. Okay, so I think this is a good point to take some questions and take a brief break. So let me first take some questions. Okay, I'm going to go from the first question here. Can we get any type of curve which does not let them meet again? In higher dimensional planes, can it not happen mathematically? Indeed, there are curves that don't meet again as well. That's right. Yeah, it's the meeting is not really the most important thing. It's really just the fact that the trajectories no longer diverge. They're you get what I mean. Like they start out diverging and they eventually end up focusing. That's really the idea. Okay. Yeah. Good. Let's see. Pringles. Okay, so this is a really good question. Why doesn't the same argument hold for, say, electric forces? In a world without electric force, I never see my charged particle again. But in a world where opposite charges attract, I do. I don't conclude space is curved. Yeah, that's a great question. Okay, and the reason is that this is a heuristic pop science argument, and you don't have enough information in this argument to really conclude that the deep things from here. Gravity is more universal than electromagnetism because you can have particles that don't carry an electric charge and but you cannot have anything that does not feel the force of gravity. That's sort of why gravity is more universal and related to the fact that space and time are curved. But yeah, it's a very good question. We'll get there. It's a great question. Keep it in mind. Is curvature possible without mass? Yeah, yeah, it is. It is. Yeah, we'll see examples of that. Yeah. And then there are more advanced questions. Are we going to dive into anti-de Sitter metric? It depends what people in later lectures want to do. I might make it a homework problem. It's not a very complicated metric, so it's a good one to look at. Okay. Okay. Now, let's see. I think that, let me think about this. Do I want to take a break now? I think that what might make sense is that I will lecture for another maybe 10 minutes, and then we'll take a break for a few minutes, and then we'll take it from there. Okay. Okay, maybe another 20 minutes, and I'll take a break. Okay. So this is quite heuristic, but it turns out it is true. Okay. As you'll see, the analogy does actually work. It's a useful analogy. Okay, but now that's all for analogies. Now we're going to actually get into the math of this. Okay, so we're going to start doing this properly. This shows you space and time are curved, but what does it mean to have space and time curved? How can space curve? How can time curve? We need some math to describe curved spaces. So that's what we're going to do now. Okay, so from now on, we're going to do actual math, and we're going to start by talking eventually about the idea of the metric, which is the basic degree of freedom in gravity. Okay. So the goal of this part is to understand how to talk about curvature. of manifolds. Okay. Now, first there's the word manifold here. Let me just briefly explain what a manifold is. You've again seen this in the pre-lectures, but I'm just going to remind you now. So a manifold has a math definition, which I'm not going to tell you, but a manifold is a space that looks locally smooth. I'm not going to define things like space or looks or even smooth. Just use your intuition. It looks, sorry. Locally means on small scales, okay, in small neighborhoods. All right. So, for example, the plane R2 is a manifold because every point on the plane is nice and smooth, and that's great. Okay. Now, here's another manifold, S2. S2 is the two-dimensional sphere. The surface of the Earth is a good example. Okay. And now, if you zoom in on the surface of the Earth, it looks flat and smooth at every point. Okay. And every surface here is locally smooth. I should say locally smooth at all points. Okay. So these two are good manifolds. Okay. I should say something which is not a manifold. So for example, a cone is not a manifold. Can anyone tell me why a cone isn't really a manifold? What's wrong with the cone? Anyone? Tip, exactly. Someone has said the tip of the cone. That's right. The tip of the cone is bad in some sense. Okay, it's a bad point. It's not smooth there. It's pointy. Okay, so you get the idea. We're not going to use anything more fancy than that. Basically, if space is smooth at all points, that means you can do calculus on the manifold, and that's what we're going to do. We're going to learn how to do calculus on manifolds, okay? The truth is, in physics, we often think about singular spaces like this. The cone is fine everywhere but the tip, and it's quite common in physics to talk about gravity on everything away from the tip of the cone, and it kind of works fine, okay? So don't be scared by this kind of thing. I just wanted to give you an example of something which is not a manifold. Okay, now, notice that this manifold looks like it's curved, and this one looks like it's not. This one looks like it's flat. Okay. And the cone is a little confusing. It turns out the cone is actually also flat, although it's not so obvious. Okay. So we need a kind of technology to deal with all this stuff. We need some math to describe it. So let's now develop the math to talk about curvature on manifolds. Okay. So given a manifold, we typically have coordinates on the manifold. I'm going to call them x mu. Sorry, I think I'm going to call them lower x mu. We have coordinates x mu on the manifold. Okay. And so really I just mean here's some manifold, okay? Just find some way to describe each point on the manifold. Put some coordinates on it. Okay, so every point here has some coordinates x mu. All right. And so mu runs over the dimensions of the manifold. Again, there is a math way to describe what it means to put coordinates on a manifold involving the words open chart and so on. I'm not going to go into that, but there's a lot of formalism for this that you can read about if you're interested. The common sense interpretation of what it means to put coordinates is actually pretty useful. It's really what we're trying to do here. Okay. So let's give you again some examples of coordinates on manifolds. So for example, consider the plane R2. So there's a very natural set of coordinates on the plane. Everyone can guess what they are. You can put, for example, x and y coordinates on the plane. Okay. Every point is labeled by an xy pair, obviously. Okay. Now, it's important to note, by the way, that there are multiple coordinate systems that you can have. So, for example, I could also put polar coordinates on the plane, right? I could put r theta. These are also perfectly good coordinates on the plane. I'm describing the same space but in different coordinates. This will be really, really important in what follows, okay? But I'll again get there slowly. And now let's look at a more non-trivial manifold. Imagine you have, for example, the sphere S2. How do I put coordinates on the sphere? Well, everyone knows about polar coordinates, right? You can put coordinates, for example, theta and phi on the sphere. Theta moves down. So if you have a point here, theta is the angle between the north pole of the sphere coming down, and phi sort of goes around like this. This has become a very messy picture. I'm sorry. But people know about polar coordinates on the sphere, right? Theta goes down and phi goes around. Okay? These are spherical polar coordinates. The important point here is there are always two coordinates because there are two dimensions on the manifold. Okay. Okay. So one more important thing, which I think you've seen already in the pre-lectures, is that the index on these coordinates at the moment is up. That actually carries some information and it'll become more important in a second. Okay. Okay. Are there any questions about manifolds before we go on? Is everyone happy with the idea of manifolds and coordinates on a manifold? Yeah. I'm seeing some questions. Yeah, sorry, I don't know what these abbreviations mean, RA and DEC, but other people have said that this is fine. Yeah. Uh, Indeed, there are many more manifoldy treatments than this. Yeah, only for lack of time, I'm not going into it in detail. Also, physicists don't really need this. So the question, mu runs over the dimensions of the manifold. Yeah, I just mean that mu takes on the number of values that mu can have is the dimensionality of the manifold. So for example, here I have two coordinates, x mu. So I can think about the zeroth component and the first component. Or sorry, let me use non-programming language. I can have x1 and x2. Okay, so x has two coordinates, x1 and x2. This is x1, this is x2. Okay, good. I hope that makes sense. How do you handle the singularities like at r equals 0 in the polar coordinate? To be honest, you just got to be careful. That's pretty much it. Yeah, you have to be careful. You have to, later on, when you do black holes, we'll realize there are different kinds of singularities and you have to be really careful about them. Yeah, good question. Yeah. Good. Dimensionality is two always? No, not at all. These are only pictures of two-dimensional manifolds because I can draw a two-dimensional manifold easily on the blackboard. The space and time we live in is a four-dimensional manifold. Okay, so is the Mobius strip a manifold? Yeah, it's locally flat. I think the Mobius strip normally has a boundary, so it depends whether you consider a boundary to spoil it or not. Some people do, some people don't. But away from the boundary, it's completely fine. Yeah, it's a pretty good manifold. Okay. Yeah, indeed, someone said it's a non-orientable manifold. That's right. We will not need that jargon for this course, but it's absolutely correct. It's a non-orientable manifold. Okay, good. Any other questions on manifolds before we keep going? Yeah. Okay. So I think actually, so we're gonna have some more formulas soon. So I think actually this is a good time to take a 10-minute break. So we're going to take a 10-minute break now and resume at 8 p.m. Bangladesh time. Okay. So we'll resume at the hour. I will stick around and take questions, but we'll start again in an hour with more math. Okay. Okay. 10-minute break. Okay. So now I'm just going to answer the questions. Michelle, can we pause the recording for this part actually? Is that okay? Okay. Thank you for the recording start. Okay. Just erasing all of these pictures. Okay, let's go. So where were we? Previously in these lectures, we had talked about coordinate systems on manifolds, and we stopped. Okay. And now the next thing to do is talk about vectors. Okay. Now, what is a vector? So the way I want you to think about a vector is really just the following thing. If you imagine you have a manifold, a vector is a vector is a little arrow pointing along the manifold. Okay. This seems a little fluffy, but it's really a good way to think about what's happening. A vector is like a little arrow. That's pretty much what you think about as a vector already. Okay. Notice that a point on a manifold is not a vector. Okay, a point is a point. All right. A vector is a little arrow coming out from that point. Okay. This is different from in flat space. In flat space on R2, we often conflate two different ideas. If you have a point on R2, you can think about the vector from the origin to that point. Okay? And often we combine the idea of the point and the vector. However, these are two different things. So from now on, I want everyone to forget about that. Points and vectors are two different things, right? It's pretty clear that if you have any manifold that's more interesting than flat space, you can no longer identify an arrow with a point. So there should be no confusion, okay? A vector is a little arrow. And now, when I say a little arrow, a slightly more formal thing to say is that this has a geometric meaning, which is independent of the coordinates that are used to describe it. Okay. So this is, I think, a very important point that we're going to keep coming back to over and over again. You see, all the concepts that we use in physics have to be independent of the coordinates that we use. You can use flat coordinates, you can use polar coordinates. You have to get the same answer for everything important. All right. This is a very basic physical principle. It's sort of amazing how much power we get from that principle. Okay. A lot of power will come from that demand that life should be invariant of the coordinates we use to describe it. Okay. So I want everyone to keep this in mind. Okay. Now, a useful way to think about a vector is to imagine a curve on a manifold. Okay. So for example, let me draw a curve on this manifold. So here's a curve moving through the manifold. Okay. So I'm going to call this curve x mu as a function of s. Okay. So s is some parameter that varies between say 0 and 1. As I go from 0 to 1, I move along this curve. Okay. Now, a good vector, a nice vector, is, for example, the tangent vector to the curve. So imagine v mu, which I define as dx mu ds. Sorry, I became a bit bolder than I wanted here. Dx mu ds is the tangent vector to the curve. This is an example of a vector. Okay. Clearly, it's a thing that points along the curve at every point. Okay. Now, so this is an example of a vector, but I'm going to use this to sort of motivate many things. Okay, as we go, this is a very simple example of a vector. Okay. Now, here again is an important point. Vectors' coordinates have different components in different coordinate systems. But the underlying geometric identity, the geometric significance, we should say the geometric identity of the vector remains the same. By which I mean a vector is an object which you can describe in different coordinates. Okay. So let's again look at an example. Okay. So here's an example. So again, I'm going to take my favorite, the plane. All right. Now, there are two different coordinate systems on the plane. There's the Cartesian coordinate system, which is x and y. Again, everyone knows this. This is the normal coordinate system on the plane. And there are polar coordinates, okay, which are r and theta. Okay. And these two are related by the following equation: x equals to r cos theta and y equals to r sine theta. Okay. Now, I'm going to be very careful here. I'm going to denote the polar coordinate system by mu with a bar on top. Okay. So x mu bar refers to polar coordinates and x mu refers to Cartesian coordinates. Okay. There is a formula that relates x mu bar to x mu and vice versa. There's this formula here. Okay. This relates the coordinates, the components of x mu to the components of x mu bar. So let me just write that down. There's a function x mu, which is a function of x mu bar. And you can typically invert this function to get x mu bar as some function of x mu. Okay. So like r is square root of x squared plus y squared and so on. Okay. Okay. And I should just draw a picture of what polar coordinates mean. Again, I think everyone knows this, but here's polar coordinates. Okay. Now, the same vector will have different components in the two different coordinate systems. Okay. So imagine that I have a curve, okay, x mu of s. I want to calculate the components of the tangent vector. If I know it in one coordinate system, I want to calculate it in the other. Okay. So let us understand the tangent vector. Okay. So first, let me think about the tangent vector v mu bar. Okay. So if I'm doing this in this example, v mu bar is the tangent vector in polar coordinates. Okay. So this tangent vector is defined as dx mu bar divided by ds. Okay. But now I want to relate this to the components in the other coordinate system, the unbarred coordinate system, x mu. Okay. So how do I do that? Well, I use the chain rule on this thing. If I use the chain rule to express x mu bar in terms of x mu, what I find is a formula that looks like this. Okay. So this is the chain rule. Okay. Again, this is just a basic calculus thing. If you sum over these things, the sort of the mu's cancel and you get the original thing back again. Okay. This thing here is called the Jacobian matrix. Okay. And it is the derivative of the barred coordinates with respect to the unbarred coordinates. Okay, is everyone happy with this formula? Let's take a second to stare at this formula. Now, one thing I'm going to stress is, look at this formula. There's an index mu that appears twice, which we sum over. Okay. It is common in this field to omit the sum. Okay. In other words, from now on, I will just write this like this. Okay. The reason you know that you sum over it is because this index appears twice, and so you sum over the repeated index. Whenever an index is repeated, you always sum over it. This is called the Einstein summation convention, and I believe you've seen this already. Einstein did many amazing things for science, and one of them is this great convention. Okay. There's a question, is it hidden summation? Yeah, I guess so. I mean, whenever an index is repeated, you always sum over it. Okay, that's what this means. Okay, good. So now this is the formula, but now what we're doing, remember, what is dx mu ds? This is v mu, right? So in other words, we have the following formula. The components of v mu bar, oh, what just happened? Sorry. The components of v mu bar are partial x mu bar, partial x mu, v mu. Okay? Because v mu is exactly this thing here, just dx mu ds. Okay? This formula is what's called the transformation law of a vector in different coordinate systems. Okay? So if you have a vector in one coordinate system, this is how you calculate it in a different coordinate system. So this is an extremely important formula. Okay? And in fact, it is so important because, I was a little bit fluffy about what a vector is. I was like, what is a vector? Oh, just imagine a little arrow and so on. The truth is, most physicists think about vectors in a slightly different way. Most physicists think that any object which transforms like this, that transforms like this formula is a vector. In other words, here is the actual physicist definition of a vector. Definition: a vector is something that transforms like a vector. Which sounds a bit tautological. What it really means is a vector is something which transforms like equation star. Okay. Now, I want to work out one simple example of this. I will not do too many examples in these lectures just for lack of time, but I'm going to do one simple example before we go. Okay. And so let's do that. Let me work out, for example, just in polar coordinates, how this works. All right. So first of all, I want to imagine the following vector field. So imagine we have the vector field in polar coordinates, which is that Vr is 1 and V theta is 0. Okay. So what does that look like? That is a vector field that points always in the radial direction, right? Okay. Now let me work out the coordinates of that vector in Cartesian coordinates. Okay. So what is this? Well, if we use this formula, we see that what we should do is take the derivative of the new coordinate with respect to the old coordinate and multiply it by the old coordinate. So in other words, Vx is partial xx partial xr times Vr plus partial xx partial x theta V theta. Okay. And just to be clear, by xx, I really just mean the x component of x. So really, I should probably just write here. Sorry, my notation is a bit clunky. What I should really just write here is this. Partial x, partial r, partial x, partial theta. Okay. Okay, now v theta is 0, so this does not matter. And what's partial x, partial r? Remember, when you go from polar coordinates to Cartesian ones, there's a formula like this. Okay. And so therefore, partial x, partial r is cos theta times Vr, which is 1. So Vx equals to cos theta. And you might want to write that in x coordinates, x and y Cartesian coordinates, in which case this is just x over square root of x squared plus y squared. That's how you write cos theta. Okay. Similarly, what you find is that Vy works out to be y over square root of x squared plus y squared. Okay. So this is, of course, also the coordinates of the same vector field, just expressed in different components. All right. So the components are different, but the vector is the same. The vector is always this vector that I've drawn here. Okay. Any questions about this? Is everyone happy with this definition of a vector? A vector is something which transforms like a vector. Oh, I see there are many questions here. I'll get to tensors in a minute. Don't worry. Now, do basis vectors have any role to play in this definition? Yes, yes. So I'm sort of taking a slightly different route to define vectors. But these are the components of a vector. You can also imagine taking those components and dotting them into a basis of things. And really, the components that I'm using are in what's called a coordinate basis, which means the basis is aligned with the coordinate system. That is the conventional basis that most people use in this field. But there are also non-coordinate bases. There's an appendix to Sean Carroll's book that explains this very carefully. Okay. Excellent question. Why not the formal abstract definition of a vector? Honestly, just because of lack of time, really. Yeah, just because, we only have so much time. So I'm trying to get us to the meat of it as quickly as possible. There is a formal definition which one could play with, yeah. And indeed, a vector is in some sense a 1, comma 0 tensor. Okay, good. Is it a basis of vectors for the curved space? Yeah, the coordinate basis is a vector in curved space. Sorry, is a basis of vectors for the curved space. Yes. Okay. So, so basically, a vector is something that transforms like a vector, which means that not all components, not all objects with the right number of components are vectors, okay? So not all collections of objects are vectors. So for example, you could put, for example, I don't know, like the pressure with the number of students in this class, okay? Here's two numbers. You could assemble them into an object with two components and say, hey, here's my vector X, or not X, I don't know, I'll call it W, it's a vector. But it's not a vector, okay? This isn't a vector, it's just a thing with two components because this object does not transform like a vector does, okay? So you can write something down with two components that's not a vector, okay? A vector must transform in this manner. Okay, next, what is a tensor? A tensor is a vector with more indices. This is again a terrible math definition, but you get the idea. Okay. So for example, a tensor with two indices is something which transforms like a vector in each of its indices. Okay. So this is a two-component tensor, and to work out its coordinates in a different coordinate system, you multiply by two factors of the Jacobian matrix. Okay, one for each index. All right. So this is a tensor. Now, finally, I want to point out something that I just did here. You'll notice that I just wrote down the formula really quickly, right? Now, that's not because I've memorized the formula. I wrote it down really quickly because there's only one form this formula could take. And the reason is the index placement is crucial. Okay? In particular, I'm writing all these vectors with indices that are up. And that means that I know that the derivative that I'm taking has the new guy, the barred guy on top, and the unbarred guy on the bottom, because on this side, the barred guy is on the top. Okay? So there is information that is in the placement of the index. The up index is not the same as the down index. And in a second, we will learn how to go from up to down indices. Okay? But the index placement is crucial. Okay? You should never have a formula that has one up index and one down index. Okay? And we'll get there as we go. Okay. So we have learned now what vectors are, and we have learned how to convert vectors from coordinate systems. So next question should be, what is the magnitude of a vector? How do I compute the norm or the magnitude? And for that, we finally need what's called the metric, which is a new structure. Okay. Oh, sorry, there's a question about contravariant and covariant. Yeah, what I'm doing right now is I think a contravariant, I think. I can really never remember. In about 20 minutes, I'll explain the difference again. Yeah, okay. So what is the magnitude of a vector? And for this, we need the metric. Okay. This metric is really the star of the show. Okay, it is the star of GR. We are going to spend years calculating it, differentiating it. You'll see. Okay, the metric is really the star of general relativity. Okay, and again, I'll introduce it slowly. So, as an example, consider flat space. So, flat space, by which I mean R2, in Cartesian coordinates. So, in X and Y coordinates. Okay. Now, imagine moving a small distance. So, move a small displacement dx dy. Okay. Oops, something just happened. So move a small displacement of your coordinates. So you imagine taking x and y, going to xy plus dx dy. Okay, this small displacement. What is the distance that you moved? The distance is that thing here. And by Pythagoras, I'm going to call the distance ds. By Pythagoras, the distance dx squared is equal to dx squared plus dy squared. Right? This is the distance that I moved in flat space. Okay. So let's abstract this a little bit. I can write this dx squared as delta mu nu dx mu dx nu, where delta mu nu in this case is just 1, 0, 0, 1. Okay. So this gives us an idea how to talk about more general spaces. Okay. And the idea is the following. For an arbitrary manifold, the metric g mu nu of x is defined as the following object. It is defined as the object which tells you how much distance you move if you do a small displacement dx of your coordinates. Okay. This is the definition of the metric. It tells you what the actual distance that you move is if you displace your coordinates a little bit. Okay. So in flat space, on the flat plane, in Cartesian coordinates, the metric is very simple. It's just the identity matrix. But in general, it is a more complicated matrix. Okay. It's a matrix which can, in general, depend on points in space and time and everything. Okay. So this tells you how to compute distances and, in fact, how to compute the norms of any vectors. All right. So imagine you have a vector v mu and you want to compute its magnitude or its norm. What you would do is the norm of that vector v mu is equal to the square root of g mu nu v mu v nu. All right. So this is how you can compute the norm. of a vector. I feel a bit wrong about putting this here. I'm going to remove the index from here because I'm computing the norm of the vector v, which is independent of the coordinates used to describe it. Okay. Okay. This is the idea of a metric. All right. It tells you how to compute distances or norms. So I'll just write that down because it's quite important. Distances and norms of vectors. Really inner products in general of vectors. Okay. We're going to see many examples of this as we go. All right. So what are the properties of this object? Well, it's a matrix. It's symmetric, which means that G mu nu is the same if you switch the indices around, G nu mu. This is probably clear, but just in case, let me just say that if you have a matrix, mu and nu, like mu runs over, so typically, let me use what's normally done. Typically, mu runs over the rows and nu runs over the columns, okay? And so this thing is symmetric, meaning that if you switch the rows and the columns, you get the same answer. G mu is the same as G nu mu. And you also want it typically to be invertible. The inverse of G should exist, okay? We will always assume that it exists, okay? And fun things happen when this inverse does not exist. Okay, so this is the metric, and it turns out this metric is the basic thing that defines curvature, all right? Not the metric itself, but some object derived from that. If you know G mu nu of X for a space, you know a lot about the space. Okay, any questions about the metric before we continue? Is everyone happy with the metric as an object? I hope so. Okay. There's a question of what about the eigenvalues? Sometimes they're important. You want the eigenvalues to never be zero, because if they are, then this invertibility thing is broken. And in physics, we often find one negative eigenvalue corresponding to time. Uh, but again, we'll get to that. Yeah. What do you mean by invertible? The metric is a matrix. I just want it to be possible to find the inverse of this matrix. That's all. Okay. In particular, if you have a zero eigenvalue of a matrix, then you typically cannot invert it. So that's why I don't want to have a zero eigenvalue. I just mean, normal matrix inverse. We have to be able to take the matrix inverse. Okay. Good. Any other questions about the meaning of the metric before we go on? Does the symmetry break down around the black hole? By symmetry, you mean this symmetry? This symmetry never breaks down. No. The invertibility actually can break down if you pick your coordinates badly near a black hole. That can break down, but the symmetry never breaks down. Yeah. Oh, this is a great question. You said that the length is invariant. Does the metric transform in a way that makes the length invariant? This is such a great question that I'm going to now take that question and go from there. So indeed, the metric transforms in a way to make the length invariant. Okay, so let's push on that. There's some other questions. Can we draw a metric? I don't know. I'm not sure. It depends on your art skills. We draw pictures. And how is G with a lower index and G with an upper index? Okay, great question. We're going to get there. Why should it be invertible? Also, great question. We're going to get there. These are all great questions. You're really anticipating the next half of the lecture. So I'm going to keep lecturing and then the question and answers will come. Okay. And can we get the PDF live notes? Yes. It's an easy question. Yeah. Okay. Good. The distance that we get from the metric, is it a distance between 2 points on the manifold? It is a distance, the metric itself tells you the distance between 2 points that are infinitesimally close on the manifold. Okay. To get a big distance, you have to integrate this thing in some way, which we'll do. Okay. Okay. Now, but let me come back to that. Does the metric transform in a way that makes the length invariant? And the answer is yes. Okay. So, um, the metric takes a different form in different coordinates. Okay. So the metric transforms. Okay. In such a way as to keep the length invariant. So it transforms in coordinate systems. Uh, Sorry, this thing, my computer has become sentient and it believes that I want to be writing in text, which is really annoying because I don't want to be. So it transforms. I'm kidding. It's not sentient, but it's the AI features are a little bit annoying. That's all. Uh, Change of coordinates formula. So we're going to derive this formula in a second. But before we do that, let's understand why the metric is different in different coordinate systems. Okay. So again, we're going to come back to my favorite example of flat space. Okay. So let's look at R2 in Cartesian coordinates. So imagine moving a small distance, this is what we just did. I'm drawing it again. Okay. And we saw that ds square is dx square plus dy square. So the metric g mu nu is just 1, 0, 0, 1. Okay. Now let's go to polar coordinates. Okay. So now let's again imagine moving a small distance, but in polar coordinates. Okay. So for example, if I move in r, then I move out this way. And if I move in theta, then I move that way. Okay, this is the displacement in theta, right? Now, what is this distance, ds square, in terms of dr and d theta? So ds squared by Pythagoras is the length of this side squared plus the length of that side squared. But ds squared is therefore dr squared plus, what is the length of this side? If this angle is d theta, then the length of this side here, this side over here, is r squared, d theta squared, right? Because this side has length r d theta. So in other words, in these coordinates, the metric is no longer the same. The metric now, if I write it down, g mu nu, is now 1, 0, 0 r squared, right? The metric depends on r. Okay. So notice that the metric in polar coordinates is not the same as the metric in flat space. They're different. Importantly, the metric in polar depends on r. Okay. And in fact, some people have been talking about invertibility and so on with the metric. Maybe I'll just mention something briefly here. Notice that at r equals to 0, this metric has a 0 eigenvalue and is no longer invertible. So something bad is happening at r equals to 0. There's a kind of singularity, but it's not a real singularity, right? I mean, space is R2. There's no singular points. And this can show you sorts of bad things that happen if you try to use coordinates that aren't well behaved, okay? So for our purposes, the fact that the metric is not invertible there is not a big deal. We're just going to ignore it and continue with our life. Okay. Okay. Now, um, so as we can see, the metric is different in these coordinates than in these ones. So let's now derive the transformation law. So I should probably call this the barred coordinate system and call this g mu bar and g nu bar. So now we're going to derive the coordinate transformation. And again, we'll just do this by equating things in the barred and unbarred coordinate system. So imagine that I have a small change in the barred coordinate system, dx mu bar. By the chain rule, this is dx mu bar, dx mu, dx mu. Okay. And similarly, we can go the other way. If you want to go from the barred to the unbarred coordinate system, the formula is this. Okay. Again, by the chain rule, dx mu is partial x mu bar, dx mu bar. Okay. Now, as we know, the metric tells us what the displacement is in one coordinate system. And it also tells us what the displacement is in the other coordinate system. But of course, these two things are equal, right? This equals to this. And the reason these are equal is because the length does not care about the coordinate system. It's called the proper length is invariant, as someone pointed out in the chat, which means these two things are equal. Okay. And now to derive the transformation law, we can just plug in. So what I'm going to do is replace dx mu in this formula in terms of dx mu bar using this relation. So I'm going to take this quantity and replace dx mu with partial x mu bar, and replace dx nu with partial x nu bar. Then I'll put back the dx nu bar. Okay. So this quantity is the same as this quantity with the x mu and x nu transformed. And now this, of course, is exactly equal. This is equal to this by hypothesis, which means that this must be equal to this. And so we have derived our transformation law. The transformation law is G mu equals to partial x mu bar, partial x nu bar, G mu nu. This is the transformation law of the metric. Okay. Now, note that it couldn't actually have been anything else, though, right? Because again, remember, the index placement here is playing a very powerful role. I have two lower indices. There have to be lower indices here, which means they must be in the denominator, and therefore these must be in the numerator, and they have to cancel in this way. Okay? So the index placement here is crucial. The index placement fixes the answer completely. It could not be anything else. Okay? So here is now a homework problem, which will be teched up for you. Homework, show from this law, this is called let me not say that right now, but show from this law, show from this transformation law, that the metric and polar coordinates on flat space is indeed ds squared equals to dr squared plus r squared d theta squared. Previously, I argued this based on like drawing little pictures, these little pictures here. I want you to prove it from the coordinate transformation from polar to Cartesian coordinates. Okay. Okay. So now we have about 20 more minutes, which is I think just enough time for you to introduce some more formalism. Okay. So we now know how the metric transforms. And now this is actually a special case of a more general formula. So I'll explain that right now. So let's next define the inverse metric in the following way. Remember, so the metric is invertible. Define the inverse metric to be G upper mu nu. Okay. So my metric is G lower mu nu. The inverse metric is G upper mu nu with the indices up. Okay. So let me write down what this means. Okay. So viewed as matrices, obviously G inverse times G is the identity matrix. Okay. Now let me write this in matrix in the index notation, G inverse is G mu nu. Okay. Now, what is matrix multiplication? Matrix multiplication says that you sum over the columns of one matrix and multiply them with the rows of the other matrix, which means that I should be summing over these columns and multiplying them by these rows. And the thing that I get afterwards is 1, meaning that if the two indices agree, I get 1, and if they disagree, I get 0, which means it's nothing less than the Kronecker delta. Okay? So this is a formula that is obeyed by the upper and the lower, that's obeyed by the upper and the lower index metric. Okay? Now, there is a reason why we have defined the inverse metric in this way. And that's because now we can sort of raise and lower indices with the metric. Okay, now what do I mean? Imagine someone gives you a vector, v nu, that has an upper index. Okay. What you can do is you can convert this into a vector with a lower index by multiplying it with the metric in this way. So this is the definition of a vector with a lower index. Okay. This is called a covariant vector. And the guy with the upper index is called the contravariant vector. All right. Someone asked about covariant and contravariant. This is the meaning. Contravariant has an upper index, covariant has a lower index, but you can always go from one to the other by using the metric. Okay. Shouldn't it be v nu? Yes, it should. I did that on purpose to check if you were paying attention, and you were. Excellent. Thank you. Yes. Okay, good. Yeah. Did I make any similar mistakes? No, the rest is good. Thank you. Good. It should be v nu. Yeah. Okay. And indeed, yes, people can call it also sometimes these are called vectors in one form. So shouldn't we write that down? You also see that in literature. Sometimes this is called a vector, and this is called a one form. Okay. But for us, the important thing is you can always go back and forth by using the metric. All right. And now, similarly, you can go the other way. In other words, if someone gives you a lower index vector, you can multiply it with the upper index metric and get an upper index guy. Okay. Did I do this right here? Yes, now it's correct. Okay. So indices are balanced. And let's just do a little bit of exploration to check that this makes sense. So imagine that you want to check these two things are consistent. What you can do is you can, for example, take this, right? And then imagine that you take, so let me write it this way. So I can now plug in this formula into here, right? And see what happens. So for example, I can write G mu nu times G nu rho V rho. So I've taken V rho and put it here. The order doesn't matter. Okay. And now what is this? This object here, from the formula that we put above here, is delta mu rho times V rho, which is only non-zero when these indices are the same, which means that this is equal to V nu, which again is this, okay? So all I'm doing here is testing that the notation is consistent. Okay, and it is, and that is why we define the inverse metric with the upper indices. Okay. Okay. Now, what is the point of this? The point of this is that vectors, or rather now I suppose they're called covectors or covariant vectors in one forms, but I'm just going to call them vectors with lower indices transform differently than those with upper indices. Okay. So for example, this formula we already saw. This is how an upper index vector transforms. This formula you've sort of seen in the example of the metric, but I'll write it down again. Okay. This is how a lower index vector transforms. Okay. Notice that it's different. This matrix is different from this matrix. Okay. This one says differentiate the new coordinate with respect to the old one. This one says the old one with respect to the new one. Okay. They're actually different. Right. And I want you to prove this in the homework from the definition here. Okay. This is all a bit circular because to be honest, it's all just baked into the formalism, but I want you to prove it from this law here. Okay. And now, finally, you can have a tensor with arbitrary numbers of upper and lower indices. Okay, so for example, you might have, let me actually write it like this. You might have mu1, mu2, blah, 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 mu p, nu1, nu2, blah, 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 nu p. Okay. This has p upper indices and make this a different number, q lower indices. Okay. This is a completely fine tensor to have. It's called a p comma q tensor. And if you want to transform it, what you do is transform every upper index like this and transform every lower index like this. So let me just write that down for you. Mu1, mu2, blah, blah, blah. Mu p bar, mu1 bar, mu2 bar, mu q bar is mu1 bar partial x mu1 partial x mu2 bar partial x mu2 blah, blah, blah. And now I transform also the lower indices, mu1 bar, blah, 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 partial x mu q bar, partial x mu q, oops, bar, all multiplied against t mu1, mu2, nu1, nu q. Okay. So this is how a tensor with arbitrary up and down indices transforms. Okay. So you have to believe me, but I didn't actually write down this formula in my notes. This one I just tried to rederive in real time from the fact that some indices are up and some indices are down. I think I succeeded. But the point is, you see, the notation really helps. Okay. As long as you get the indices contracted in the right way, there's really no way to write down a wrong formula. Okay. So in particular, when you're writing down a formula, always contract indices one up and one down. Okay. So for example, this is okay because we have one up index and one down index. This, on the other hand, is not okay. Okay, this is wrong because it has two up indices. You should not write down a formula like this because if you do, it will not actually be invariant if you change coordinates. So this is not a good geometric formula. This is. This formula, in fact, just makes me uncomfortable to look at. It really genuinely makes me feel a bit queasy. I'm going to sort of scratch it out. And I hope that you will have the same feeling after working in this in a while. You'll realize that you should never write down something like that. Okay. So notation is very, very helpful. Okay. Are there any questions about this before we continue? I see there are a few questions. One of them was, isn't it the vector components? I don't quite know what that means, but probably yes. How to interpret index lowering, raising geometrically? That's a very good question. The truth is, there is a sort of geometric interpretation. Um, Vectors and one forms kind of have opposite meaning in that vectors are kind of like derivatives in a certain direction, and one forms are kind of like level sets of coordinates. I have not found this that useful for me operationally, but there's a book by Misner, Thorne, and Wheeler that really pushes on this. So I can put that in the Slack if people are interested in that. Okay. Can you upload homework on the Slack? Yes. If two up indices appear, we should still have Einstein summation applied. So my point is that you should never have two upper indices that are the same. So you should never get this. Okay, this should just never happen. All right. So don't do Einstein summation. Just be like bad. Okay, that's what should happen. Yeah. How do we define dot product? That's a very good question. This is actually the dot product. Okay. So if you have two vectors and you want to take the dot product is V mu W nu contracted with the metric. This is the invariant dot product, okay? But I want to point out there are many ways to write this now. This is the same as this, which is the same as this, which is the same as this. These are all exactly the same formula, okay? So they all satisfy my rules. I'm always contracting one up, one down, one up, one down, one up, one up, sorry, one up, one down, and another one up, another one down. Okay, so these are all the same. All right. So this is the right way to think about a dot product between two vectors. As long as you follow these rules, the answer you get will always be independent of coordinates. Okay. Um, could I describe what is meant by metric as the fundamental degree of freedom? Yeah, I'll get there a little bit as we go. Can we think of lower index vectors as the row matrix and upper index as the column matrix? You often can. I'm not sure this is that important. You see, the rows and columns are basically the way that we write them down if you want to write them down as a table of numbers in your notebook. But it's kind of, I think that's not really that important, except unless you're doing a calculation. So I wouldn't dwell on that too much. And which book should you follow to study elaborately and thoroughly? There are many books on this. I like Sean Carroll's book called Space, Time, and Geometry. I'm sort of following him a bit faster here. Yeah. Okay. So I'm almost out of time. I just want to write down a few more interesting metrics before we go. Okay, so I'm going to give you two examples of slightly non-trivial metrics. So first, I'm going to give you the example of Minkowski space. So this is the space that we live in, R1, 3. And this is the metric of our space-time. And the metric is minus c squared dt squared plus dx squared plus dy squared plus dz squared. This is the metric for the flat space that is invariant under the transformations of special relativity. C is the speed of light. And from now on, we're going to typically set c equal to 1, which means the metric is minus dt squared plus dx squared plus dy squared plus dz squared. As a matrix, it is minus 1, 1, 1, 1 with all else 0. Okay? This is the metric of flat space-time. This minus sign is there because time is different from space. Okay? So these are the spatial coordinates. This is the time coordinate. You have all encountered this already in your special relativity reviews. Now I'm just telling you it's a special case of a more general thing. Okay? The question, why is C taken to be 1? And that's just because it makes life, you have to stop carrying it around. If you want to put it back, you can always put it back. What we're saying is I am measuring space and time in the same units. In everyday life, we measure time in seconds and space in like meters because that's basically because we move very slowly compared to the speed of light. But for beings who move fast close to the speed of light, they would measure space and time in the same units because they're just different aspects of the same thing. Okay, so we're going to take C to 1. You can always put it back afterwards if you want to. Okay, and now I want to finally, I've talked a lot about curved space, but I haven't actually done any curved space. I've just been doing flat space in polar coordinates and so on. So here's your first example of a metric of a curved manifold. And this metric is going to be S2, the sphere. So this looks like this. And again, I'm going to take theta to be the coordinate that goes down like this, and phi to be the coordinate that goes across. And the metric of the sphere is the following: d theta squared plus sine squared theta d phi squared. Okay? This is the metric of the two-dimensional sphere. Okay? Notice that it depends on theta. You might say, well, we saw this already. I mean, when you wrote down the metric in polar coordinates for flat space, it also depended on r. But over there, we could always change to a coordinate system where it didn't depend on anything. And that's because the space was actually flat. Over here, the space is not flat, which means we can never find coordinates where the metric is constant. It will always depend on one coordinate or the other. Okay. Now, let's just take a second and understand why this metric takes this form. You see, theta moves us down this way, okay? And movement in theta always gives us some distance that's non-trivial, but the amount that you move in phi depends on where you are in theta. You see, if you are at this pole and you move around in phi, nothing happens, right? You don't actually move through any distance. And that's why when theta equals to 0, which is happening here, movement in phi does not actually move you around at all because the sine theta factor is 0. If you make theta bigger and bigger and bigger, over here we are at theta equals to pi on 2 on the equator. And now if you move in phi, movement in phi does change something. Okay? And finally, if you make theta bigger and bigger still, when you're at theta equals to pi on the south pole, again, movement in this direction doesn't do anything at all anymore, which is why the sine square theta again goes to 0. So this sine square theta is just capturing the fact that the sphere is bigger and smaller again. All right. This S1, this phi circle gets bigger and smaller. That's what's happening here. So it's quite reasonable this should be here. And the point of this example is to show you that the dependence of this metric on the coordinates captures the fact that the sphere kind of bulges out in the middle, which is of course what it means to have curvature. Okay. Okay. So I am now out of time, but in the next lecture, we will discuss, or rather Nafis will discuss sort of more stuff on vectors in curved space. And in particular, you might ask, how do you take derivatives? And it turns out that concept also has to change, as you'll see in the next lecture. Okay, we are out of time. Are there any quick questions before we conclude? Maybe we can stop the recording now, actually. Yeah, I'll stick around.